Hello, everyone. Welcome back. We have a new chapter to start the week off with, and it is chapter 13 in our book on states of matter. So you guys already know a lot about the states of matter. You start learning this way back in elementary school. So what we're going to focus on is a little bit more around why. Not just their properties, but answering that question why, which is why one of your assessments for this chapter will be a claim evidence reasoning type question. So this first table here, taken from another textbook, but this goes over what is just the characteristic properties of the different states of matter. And most of these you already know. I'm just going to highlight a few of them, mostly which ones there may be in common. One thing is compressibility, right? So when we look at liquids and solids have a lot of the same characteristics in that they are virtually incompressible. It means you can't take and make the volume any smaller, and they do not expand to fill its container. And then if we look at gases and liquids, what do they have sort of in common is that gases and liquids both flow readily. If you pour out a gas, it's weird because we don't see that because we can't really see gases, but they do pour and flow the same way that a liquid does. Okay, so these are just some of the properties of the different states of matter. And then I will use this graphic on the left and on the right often when we talk about the three states of matter. So this is some information that you already know, that a solid is where the particles are very close together and they are not moving. They are vibrating. That's what this little sign is for. They're vibrating, but then this particle never moves over here. We know a liquid, they're vibrating more and they're moving, but they're still very close together. And a gas, obviously, they are moving more and they're very far apart. And what is the difference is how much energy there is. Often, energy is analogous to temperature. So the higher the temperature, the more energy the particles have, and that can change their state of matter. So what if, think about everything that is in your house right now on your table that you're looking at, right? The air in the room is a gas. Maybe the water in your water bottle is a liquid, and the chair that you're sitting on is a solid, but they're all at the same temperature. So what's going on there? It's all about this energy of attraction. Those are the two things that really make a substance a particular state at a given temperature. That in a gas, the kinetic energy of the particles is much greater. That's what this symbol right here is stating, that the kinetic energy of the particles is much greater than the energy of attraction. That can happen because it's at a really high temperature or because the energy of attraction is really small. Right? Even in the middle of the winter, the air is still a gas. The particles don't have a lot of kinetic energy, but their energy of attraction is so small that the kinetic energy is much larger than the energy of attraction. In a liquid, they're around the same, and in a solid, it's the energy of attraction that is much larger than the kinetic energies of the particles. Right? If you take an aluminum beach chair to the beach in the summer, that aluminum metal gets very, very, very hot, but it still stays a solid because the energy of attraction between the particles in aluminum, between the aluminum atoms, is very strong. We'll do basically 13.1 is all about gases, 13.2 is all about liquids, and then we start getting into a little bit more about solids and then phase changes. So those will be sort of our videos. So the nature of gases here, we will start with looking at something that's called the kinetic molecular theory, KMT. And when you are doing your your claim evidence reasoning, this could be, this is going to be, a good place to find some evidence. This is basically, what do we say gases are? What are gases? Gases consist of large number of molecules that are in continuous random motion. Their combined volume of all the molecules of the gas is negligible. Remember that word negligible, too small to make a difference. That's what that word means. Relative to the total volume in which the gas is contained. What does that mean? That means if you took the actual molecules of air, oxygen and nitrogen, in this room and took out and measured the volume of them, it would be incredibly small compared with if you measured the length, width, and height of the room that you're in. Another one is that the attraction and repulsive forces between gas molecules is negligible. We know that all molecules are attracted to each other. Those are called intermolecular forces. Sometimes intermolecular forces are big, sometimes they're small. Well, that's what we're looking at here. Are they negligible? Energy can be transferred between molecules during collisions, but the average kinetic energy of a molecule does not change with time as long as the temperature of the gas remains constant. So in this room right now, there are molecules of nitrogen and oxygen, and they're constantly colliding with each other. But they transfer energy from one molecule to another molecule, but the overall energy that those molecules have, right? The average kinetic energy of the molecules is proportional to the temperature. So an individual molecule can change energies, but the overall average will stay the same if it's the same temperature. And that's what number 5 is talking about. The average kinetic energy is proportional to the absolute temperature. The word absolute temperature, if you're wondering, what is that? That means Kelvin. Where 0 actually means that it has no kinetic energy. Right? When a molecule is at 0 degrees Celsius, it still has a lot of kinetic energy. If a molecule is at 0 degrees Fahrenheit, it has even more kinetic energy. So I guess that's not true, it has less, but they still have very little. They still have some kinetic energy. That's why we have to say that the average kinetic energy is proportional to the absolute temperature. So how do we describe gases? We describe gases in terms of 2 things. Well, we're going to talk about their volume. We're going to talk about their temperature. And we know what volume and temperature mean. Now we're going to talk about pressure. What is the definition of pressure? Pressure is a measure of the force exerted on a unit area. And what is this force? The force is, oh, look at this. I forgot those 2. What is this force? The force is when the particles collide with the walls of their container. The collisions of particles with walls of container. And look at this picture right here. This is demonstrating, if the molecules were large enough to see, this is what we would see. The pressure inside a container comes from the collisions of gas molecules with the container walls. Think about when you blow up a balloon. If you can kind of think of this balloon here. What is actually going on is that the molecules of nitrogen and oxygen and any other molecule in there, like helium, if it's a helium atom of helium, if it's a helium atom or carbon dioxide molecule, colliding with the walls of the container. Now we know molecules and atoms are extremely small. Do they really exert much force? Well, one molecule doesn't, but when you have moles of molecules, they can. How do we measure gas pressure? Well, you may have heard this term before, but that's what a barometer is. A barometer is just an instrument used to measure atmospheric pressure. you may have heard in like a weather report, you may have heard the weather person talk about using a barometer or the barometric pressure. Basically, how a barometer works is an inverted glass tube that there's no air inside of it. That's why it's a vacuum. And it's usually inverted. It's often inverted into mercury. This would be literally the liquid metal mercury. And the air molecules collide with the pool of mercury and basically push this column of mercury up. And if we're on, in high altitude like Mount Everest, where there is actually less air molecules, there is less air pressure, and they can push the tube of mercury, or the amount of mercury in the tube, up a lesser amount. So at sea level, what we would call normal atmospheric pressure is it would push a column of mercury up 760 millimeters, right? Remember, 1,000 millimeters is a meter, so this is a little bit less. And now this is the only mathy stuff that we have this entire chapter, is converting between the three different units of pressure that we use. One ATM, or I should say ATM, the unit of pressure that is ATM, atmospheres. This is the one that chemists use a lot. And one ATM, or atmosphere, is exactly equal to 760 millimeters of mercury. That's like from the barometer. Chemists will also use that. And a synonym for millimeters of mercury is a torr. And this is the SI unit for pressure, kilopascals. So you'll see that sometime, and that is used a little bit more often in physics. So we're just going to have a few questions here where we go from from one unit of pressure to another unit of pressure. So the first one says, what pressure in kilopascals, so circle the do, and atmosphere, we got two things to do in this problem, does a gas exert at 385 millimeters of mercury? So 385 millimeters of mercury, right, using the conversion factors that are up here, I know that 760.00 millimeters of mercury are exactly equal to 101.325 kPa, kilopascals, right? Multiply by the top, divide by the bottom, significant figures. This guy has 3, this guy has 5, this guy has 6. So my answer is going to be 513, lowercase k, capital P, lowercase a. That's kilopascals. Okay, and then the next one here, it says and atmospheres. So I'm going to take, that's not what I want. Back. I'm going to take my 385 millimeters of mercury and convert that to atmospheres, right? 1 ATM exactly, so significant figures don't need to worry there. And 760.00 millimeters of mercury. Okay, I did not do this one out. I got to do this. 385 divided by 760. And again, with the three significant figures, my answer is going to be 0.50. It's 65, so I'm going to round it up to 7, and that's ATM, right? This is also in the Show Me's, which is in the Schoology materials folder. So you can just see me explain it a little bit differently there. The next question says, during Hurricane Katrina, the air pressure in the eye was found to be 26.85 inches of mercury. Now, if you listen to a weather report, they will often report the atmospheric pressure in inches of mercury because we're in the United States and we don't use millimeters. So my question is, how many ATM, atmospheres, is this 26.85 inches of mercury? In order to do that, this is another conversion factor that we are going to need to use. That 1 inch is exactly equal to 25.4 millimeters. So what I'm going to do is I'm going to take my inches, convert it to millimeters, and then I'm going to take my millimeters of mercury and convert it into ATM. So I'm going to start with 26.85 inches of mercury. You'll often see that, and a lot of people think it means in mercury, but it's the abbreviation for inches. 1 inch is equal to 25.4 millimeters. And then 760.00 millimeters is equal to 1 ATM, right? Look at how the inches cancel out, the millimeters cancel out, and what do we got here? This should be also millimeters of mercury, so the mercuries will cancel out. Plug this in, 4 significant figures, because remember, this does not, the 25.4 does not count for significant figures. So 0.8974 ATM. Bad weather, things like hurricanes, have really low atmospheric pressure. And then as we wrap up, we're just going to wrap up for today real quick. The kinetic energy and temperature, how are they related? We know that as kinetic energy increases, temperature increases, right? Kinetic energy is the energy due to motion, the motion of the particles. And as kinetic energy increases, temperature increases. As kinetic energy increases, temperature also increases, but it doesn't actually increase in the same way. So look at this picture here. This is going to become a very important picture. The green line, and if you're doing this and you printed it out in black and white, you may want to just somehow mark them as being different from each other. The green line here shows like cold water. And you can see, this is very interesting, that the peak, corresponds to a certain amount of kinetic energy, but there are lots of molecules, even at cold water, that have kind of high kinetic energy. And there are lots of molecules at low kinetic energy, but most of them, that's what this y-axis is, the percent is in the middle there. And then if you look at what happens when I increase the temperature, right, a higher temperature, the peak changes, but you can see even at high or hot water, yep, more molecules have a lot more energy, but there are still, even hot water, some molecules have very little kinetic energy. So it's not that the temperature relates to the kinetic energy of every single particle. It's the kinetic energy is the average. That's really where this peak comes in, right? At low temperatures, look at where the peak is, low kinetic energy. At high temperatures, look at where the peak is, higher kinetic energy. But there's a wide distribution of that. That's going to become important when we start talking about evaporation. Think about when you spill water on the floor, and let's say you never clean it up. That water eventually evaporates, becomes a gas. How can it become a gas if we don't go anywhere near the boiling point of water? But it does, and we'll explain that more. With this. So that is basically what we're doing for. Just the first section of notes. Fudge. And so tonight for homework, or the homework after this video, in your homework packet is the notes, I've labeled them as 13.1, 13.2, but basically what you're doing today is numbers 1 through 13. You can see there's a few of those conversions of ATM to millimeters of mercury, or torr and kilopascals, but it's a lot of multiple choice and true and false. So you guys know the deal. Watch the video, take the notes, do the homework, check your answers, and then Check into a Google Meet next week to ask any questions. Have a good rest of your day. Bye.